Magnetic field patterns. Field patterns exhibited by different magnets is determined by the field lines around the magnet. Magnetic field lines refers to lines of force that originate from the North Pole and ends at the South Pole. Lines of force that originate from the North Pole of magnets. The behavior of the field lines depend on the shape of the magnet, and the resultant lines forms the field patterns. We also note that due to shapes, U-shaped magnets and horseshoe magnets are stronger than a bar magnet because their shapes allows them to concentrate magnetic field lines of force. The field lines of force exhibits the following properties. They are imaginary lines that move from North Pole to South Poles. Two, the field lines of force are parallel and never intersect. The field lines are closer together for strong fields and further apart for weaker fields. The lines leave the North Pole and ends at the South Pole at right angles. Leave and enters poles at right angles. Testing polarity. In order to determine the polarity, we use a magnet with known polarities. So in this case, we are determining the polarity of a magnet with unlabeled ends. We bring the material close to the ends of the North Pole, followed by the South Pole of the magnet, and observe what happens. An attraction when the material is brought closer to the South Pole implies that the unknown end is a North Pole. An attraction when an end is brought closer to a South Pole implies that the end is a North Pole. Repulsion when an end is brought closer to a South Pole would also imply that that particular end is a South Pole. All these observations are based on the law of magnetism. However, in determining the polarities of a magnet, it is important to note that attraction will always occur between a magnet and any other magnetic material, even if it is not magnetized. Therefore, it is only possible to conclude that a polarity of a material is either a North Pole or a South Pole when repulsion occurs. Or in other words, repulsion is the sure test for polarity. Let us now look at different field patterns between poles of magnets. We have case 1, where a North Pole is brought close to a South Pole of a different magnet. From this diagram, we observe that the field lines moves from north to south in a regular manner. However, when two norths are brought together, a repulsion experienced is shown by field lines trying to repel one another. Such a repulsion between fields leaves a point between the two poles, point X, which is called neutral point. The same point will also exist between two south poles. Neutral point is a region between two like poles where the net magnetic field or effect is zero. Where the net field effect is zero. What it means is that the magnetic field effect is not felt at that particular point. It is important to note the direction of motion of the field lines when two north poles are brought close to one another and when the two south poles are brought close to one another. For the south poles, the field lines are moving towards the poles, while for the north poles, the field lines move away from the poles. In both cases, repulsion is experienced, leaving a neutral point. Let us now look at something that is briefly or closely related to the movement of the field lines. This is what we call magnetic shielding. Magnetic shielding refers to creating a barrier on the path of the magnetic field lines of force. So if we happen to have two poles, the north pole and the south pole, the field lines will move from the north pole towards the south pole, but as a result of the shielding effect brought about by the soft iron bar, the soft iron bar concentrates the fields and allows the field lines to pass through it, as shown in the diagram. So as stated earlier, magnetic shielding refers to creating a barrier on the path of field lines. However, shielding can also be done using soft iron ring. In the same case, we note that the magnetic field lines moves within the ring, leaving the area where we have the space. The area where we have the space is said to be shielded. So the field lines move within the rod, the iron ring, leaving the shielded area. Avoids the shielded area.